By definition, the best way to increase evolutionary fitness is for an animal to be in a place where its probability of breeding success is highest. So, how to accomplish that? In theory, breeding success should be highest when an animal is in a place with the most resources. Resources like food and shelter, which an animal can use to feed and house themselves and their offspring. But instead of getting into the specifics of what those resources are, we're just going to generalize here and say that, in theory, a place has some fixed amount of resources that are useful for an animal. According to ideal free distribution theory, the number of animals in a patch should be proportional to the amount of resources in each patch. Here, a patch means like a chunk of habitat. A patch could be a farm, or a puddle, or a petri dish. So here's a patch, and it's really great. You could fit a lot of individuals in this patch. But if you put in too many individuals, there would be a lot of competition between them for these resources. So an animal might fare better if they choose a less good patch because there are fewer other animals to compete with. And that pattern continues. As patch quality decreases, the number of animals in each patch also decreases. But of course, for this to exist in the real world, there are rules. First of all of these animals need to be actually moving independently and trying to find the best patch. The animals need to be mobile enough to see and go to all the patches, and the animals must have the cognitive ability to compare the patches. It turns out that we don't always see an ideal free distribution play out simply in nature, even if these rules are followed. And that's okay. The point of a theory like this isn't to describe all of nature exactly how it happens. Instead, the value of a theory like this is to present a null model. If animals are distributed as the ideal free distribution predicts, then okay, we understand that they are following resources and avoiding competition in this simple way. And if we observe that a population of animals isn't distributed this way, then we know that something more complicated is happening, and we can make hypotheses about what that complicated thing is. In nature, the complication of animal habitat decision boils down into three options. Animals can stay where they're born, they can leave, or they can leave and then return again. Lots of different animals do each of these options, and each option has costs and benefits. Option 1, stay where you are. Animals can defend a territory like this South China tiger. This tiger is performing a behavior called patrolling, which means it's walking around the boundaries of its territory looking for invaders to kick out. Defending a territory is a pretty costly thing to do. Behaviors like patrolling take a lot of energy, so an animal who does it needs even more resources, like food, to fuel all this walking around. Defending a territory also comes with the risk of injury, as animals may have to fight potential intruders. Of course, there are also lots of benefits to defending a territory, like having a monopoly of resources in that territory and also having the option of sharing those resources with potential mates. A principle to keep in mind here is economic defensibility. When defending a territory, it makes sense for an animal to make an economic choice, which is one where the benefits outweigh the costs. While the term economic defensibility refers to territoriality specifically, this principle makes sense for the evolution of all animal behaviors. Benefits should be greater than costs for a behavior to evolve under natural selection. With that being said, animals that are defending a territory usually get to keep it. There's an interesting pattern in nature. When an invader tries to take a territory from a resident who already lives there, the resident nearly always wins. Why? One hypothesis for why residents nearly always win confrontations with potential invaders to their territory is the resource holding potential hypothesis. Resource holding potential is the fighting ability of an animal. By fighting ability, I mean traits like size and strength. Individuals that have a high enough resource holding potential to maintain a territory are likely to be strong enough to win a fight against potential invaders. Motivation to win a fight is usually described as separate from ability to fight. However, residents who already defend a territory are also more likely to be more motivated than invaders in a fight for that territory. The payoff asymmetry hypothesis explains that residents who have spent a long time in their territory are more motivated to keep it, because they gain more from keeping it than an invader would from invading it. Residents are more familiar with their territory and its various benefits, and they may already have offspring and mates that live there. Residents are likely to be more motivated to maintain their territory as they age, so sometimes old animals win fights against younger and stronger invaders just because the old one wants it more. Animals' second option is that they can leave the place that they were born in. As a downside, Leaving costs these animals some energy and takes some time. There are also a bunch of risks involved, like the animal exposing itself to predators while it tries to find a new place. And for all that work, there's no guarantee that the animal ends up in a better place than where it started. So why try? There are many benefits to dispersal. The animal can leave competitors, like in our ideal free distribution model, and they can also avoid the infectious diseases that tend to spread around when a bunch of animals are all clumped in the same place. And the biggest benefit is that an animal who leaves their birthplace increases their chances of finding a mate who isn't a close family member, which means they're more likely to have stronger, healthier offspring. Avoiding inbreeding is so beneficial that many species exhibit sex-based dispersal, where one sex of the species disperses farther than the other sex of the species. In Belding's ground squirrel, which is pictured here, males disperse and females stay put, defending their territory. The third option is to leave and come back again, which is called migration. Migration usually takes place on an annual basis, so that animals can take advantage of seasonal fluctuations in resources while avoiding seasonal changes in probability of predator encounters. However, migration takes a ton of energy, especially for the most committed migrators. For example, Arctic terns like the one pictured here can migrate up to 56,000 miles round trip each year. That's the longest migration in the animal kingdom. To illustrate how long that is, consider that it takes an airplane about 17 hours to get from Houston to Sydney. You could take that trip 6 times, and it still wouldn't be as long as the distance an Arctic tern flies in 1 year. And an Arctic tern's flight is powered by flapping wings, not jet fuel. So migration behavior is pretty impressive. And like all impressive behaviors, it's important to consider that Arctic terns probably wouldn't take on this enormous flight unless the benefits of doing so were more valuable than the costs. Impressive behaviors like Arctic tern migration give us the opportunity to make hypotheses about natural selection theory. What are the proximate and ultimate factors involved in the evolution of behavior as elaborate as a 56,000-mile migration?